Section 5.5 is going to be on graphing quadratic functions. In the video notes, we're going to be looking at specifically polynomial functions and first, squares. So we're going to graph those quadratics. We are going to see just a few more in the video notes than the rest of the sections. We're going to do some squares and some cubics here. All right. So first of all, what we want to do is graph this function here, f of x equals x squared. So we're going to just fill in the table, plugging each of these values in for x, so squaring them. Negative 4 squared is positive 16, 9, 4, 1, 0, 1, 4, 9, and 16. Again, just taking each of your x values and squaring them. The negatives turn positives because when you square something, you have two negatives, turns into the positive, etc. So I'm going to graph this real quick. So negative 4, 16, so that's right up here. Negative 3 and 9, 2, 4, negative 1, 1, 0, 0, oops, 0, 0, sorry, I accidentally did 0, 1, I was just going on a roll there, X that one out, 0, 0, then 1, 1, 2, 4, 3, 9, and 4, 16. Okay, so when you plug in the negative numbers, they're going to continue to increase higher and higher on the left-hand side. When you plug in the positive numbers, they're going to increase higher and higher on the right-hand side. So we're going to get these two tails going all the way up, depending on which value you plug in. So if I draw through all my ordered pairs right here, we see the shape of our graph for x squared. Okay, so a couple things to note about this graph. First of all, its domain. You can plug in any number, either negative or positive. It didn't matter whole number or fraction. We just plugged in the whole numbers for ease of evaluation. So the domain of this is going to be all real numbers. So I'm going to list this in interval notation first. I can also write it in set notation with that capital R with double bars. Okay. Range. Okay, so when I plug in absolutely anything, there are a set of values that I don't get out. Specifically, I don't get any negatives, right? My graph is all up here. It's not down below the x-axis. I will never have negative y values coming out. 0 is the smallest y value, and we do get 0. When 0 is squared, we get 0. So never any negatives. So the range is going to have 0 as its lowest value, comma going up to infinity. We always have a parenthesis around the infinity because it's not achievable. It's an idea, not an actual number. 0, though, is actually included. You can see 0, 0 right there as one of your ordered pairs. It is included as a y value, so it needs to have a bracket to indicate that that y value is included. All right. Now, again, we have our two notations that we're going back and forth with, our interval notation and our inequality notation, or set notation. Our inequality notation for this one would be y greater or equal to 0. All right. Now, again, if you did set notation uses the inequality. It just formalizes it a little bit more. So the full set notation would be the set of all y such that y is greater or equal to 0, but we usually use the inequality notation just because it's a smidge shorter to write than that full set notation. The set notation doesn't add a whole lot to us right here. So if I refer to this one as set notation instead of inequality notation, I'm just shortening that a little bit. All right. So if I take my page and move it up a little bit, we have some characteristics of graphs of quadratic functions down here. First, we see that the graph of a quadratic equation is called a parabola. Like the graph of a linear equation is called a line, the graph of a quadratic is called a parabola. A parabola is the name for this shape, this U-type shape. It's called the parabola. We see that word again down here. If a parabola opens upward, like this one does, then it has a lowest point, or minimum. So that's that U shape opening upward. You have your lowest point or minimum. Or if your parabola opens downward, you'll have a highest point or maximum. regardless of whether it is a minimum or a maximum, we can talk about that point singularly and call it the vertex. So all parabolas have a vertex. You use the word vertex if you're not sure yet if it's going to have a maximum or a minimum. But the vertex is either the maximum point or the minimum point. It's a turnaround point for the parabola. So the vertex here is the minimum. Okay, so that's just the word in general that you use for either the minimum or the maximum. The last characteristic about parabolas that we don't see in the linear case is that parabolas are symmetric. And you can see that above. The parabolas are symmetric. You're getting the same y values for equally spaced points across the x-axis. You have that symmetry there. And that's actually how I was able to draw the dots on the right-hand side much more quickly than the left-hand side, because they could already see how high they had to be from when I counted them up before. Okay, so they're symmetric. And the line, the invisible line that they are symmetric around, is called the axis of symmetry. So the invisible vertical line that passes through the vertex is called the axis of symmetry. All right, so those are our characteristics of the graphs of quadratics or of parabolas. Let's take a look at the next page. Now, we've got two forms that we're going to see our quadratic functions in. The first one is standard form. And in standard form, I actually thought vertex form was first. Hold on. All right, I think I was thinking about our in-class activity. So let me go back into our notes right here. We're looking at the standard form of a quadratic function. If it was linear, we'd say mx plus b. If it's quadratic, f of x equals ax squared plus bx plus c. That's the standard form. The expanded form. There also will be a vertex form that we're going to be talking about in class, and I'll just mention it up above. And that vertex form for a quadratic would be a times x minus h squared plus k. So it's just a difference about where the variable is, if the square and the x are separate, or if the variable is inside the square as a unit. They're both quadratics. I apologize, that was up too high. I didn't look on my screen. So they are both quadratics. They're just two different forms that we can write a quadratic in, and we're going to be exploring both of these forms when we get to class. All right, now back onto the standard form and some notes about the vertex. If we're in standard form, the vertex can be found using this formula. This formula says that you use the b value and the a value to compute the x coordinate of the vertex, negative b divided by 2a. Then you take whatever that value is and you plug it back into your function to get the y coordinate. That's what we're saying right here with that formula for vertex. Okay, so there's a formula for how to find the vertex, and then there's also a statement down here that we can tell what kind of vertex it's going to be, specifically based off of that a value. So if the a value is a value that is greater than 0, then the parabola opens. So for a clue real quick, we saw x squared on the previous page, and it opened up. And that has an a value of 1, because it's 1 times x squared. So if the a value is greater than 0, the parabola is going to open up. That means if it opens up, it's going to have a minimum point. All right, so a positive a value means a minimum, because it opens upward, has a minimum point. Versus the negative a value less than 0, means that your parabola is going to open down. And if your parabola opens down, it has as its vertex a maximum point. Now, I do want to point out that this is true about the a values if you are in standard form. This is also true about the a values if you are in vertex form. So the a value in both of these formulas is going to do the same job in determining if you're going to have a maximum or a minimum point as your vertex. Doesn't matter which form, they have the same a value. Now, b and c are different. You notice that we don't even use letters b and c in vertex form, but the a's do share the same rule. Okay, so just an example right here running through how to find the vertex. I've got a parabola I'm sorry, I should say a quadratic. I know its graph will be a parabola, but I have a quadratic equation here, and I want to find the vertex by hand and then talk about what kind of vertex it is. So the a value is -1 is the coefficient of x squared, -6 is the coefficient of x, and -4 is the c value. Find the vertex. So the x coordinate is -b over 2a. It's going to be -6 divided by 2 times -1. That is 6 divided by -2 or -3. All right, then I go ahead and f of -3, I plug that into the function. So that is -3 squared minus 6 times -3 minus 4. So if I calculate that, it's -9 plus 18, so that's 9, and then minus 4, that should give me 5. Okay, so my vertex is the ordered pair -3, 5. That would be our vertex. Now what kind of vertex it is comes right from just the a value. Since the a value is negative, less than 0, I know my parabola opens downward and has a maximum. So I need to explain. So I say it's a maximum because the a value is less than 0. All right. In example 3, we've got a few questions that we would like to answer based off of the graph of a quadratic. Again, just to re-emphasize, there were 2 forms I discussed. We'll talk about those again in class. There are 2 ways to write the equation, but regardless of how you write the equation, your graph will be a parabola. So in the next example, I have an equation that I don't know the formula for, but I see its graph, and I can answer some questions about it. First, f of -2. So -2 being the x value, if I trace that down, it's actually a little hard for me to tell. I don't believe it goes through at -4. It looks like -5 is where it's going to be going through. I'm going to call that one -5. Okay. As a check for symmetry, we can see the axis of symmetry, which is not specifically asked here, so I can go ahead and look at it. It looks like it's going through 1. And so 1, 2, 3 spaces away, 1, 2, 3 spaces away, it does look like I'm going through that same y value. So that's one way to check to see if your grid and your pixels aren't matching up. You know, check just 2 places instead of 1 to see if that looks like it's at that whole numbered ordered pair. All right, f of 3. So I'm plugging in 3 as an x value. It's going to be hitting right there at 0. Find x when f of x is equal to -5. Okay, this is a y value now of -5. And so I want to make note that there are those 2 x values that we need to list. So the x values will be -2, and they will also be 4. When you're given a y value for a quadratic, there may be more than one x value. When x is equal to 6, okay, there are none in this case. You are never going to reach 6, so there are none or no solution. And it's possible there would only be one solution if they were asking you for the vertex, right? So you would have 2 solutions anywhere where the graph is present that's not the vertex, 1 at the vertex, and none on the other side of it. If you have other questions at the bottom, find the y-intercepts question mark, S. And so y-intercept, in the y-axis, there's only going to be one of those. It's going to be at 0, 3. So even though it says intercepts with the S, it's never going to have 2 for y-intercept. X, though, can, because my x-intercepts right here are at 0. The x value I need to list first. It's going to be at -1, 0, and at 3, 0. Okay. So you'll never have more than one y-intercept, but you could have 2, you could have 1, you even could have no y-intercepts if your graph was all the way down, for example, and never went through. Okay, vertex. So that's my top point up here. It is 1, 4. And max or min, in this case, it's a max. I don't have an equation here to know the a value, but I know that if I were to write an equation, I would expect it to have a negative a value.